Proper installation of an isolated ground circuit involves specific steps at both the power source, which is the main breaker panel, and at the device, which is the receptacle location. Materials needed include 12.3 non-metallic sheath cable with ground, an isolated ground receptacle, and optionally a metal junction box. Firstly, at the power source, the main breaker panel, identify an empty circuit breaker slot in the load center. Secondly, remove the knockout plate that corresponds to the circuit breaker location. Thirdly, insert the 12.3 cable through the knockout and strip about 6 inches of insulation from the conductors. Fourthly, connect the white wire to the neutral bus bar. Fifthly, connect the black wire to the load side of the new circuit breaker. Sixthly, connect the green, or bare, wire to the main ground bar or isolated ground bar if available. Now consider the work at the device, the receptacle location. Firstly, mount the metal junction box, optional, at the desired location. Secondly, connect the red wire from the 12.3 cable to the brass screw on the isolated ground receptacle. Thirdly, connect the green, or bare, wire to the green grounding screw on the receptacle. Fourthly, connect the black wire to the black screw on the receptacle. Fifthly, connect the white wire to the white screw on the receptacle. Now for verification at the panel, ensure that both the red and green, or bare, wires are connected to the ground bar. At the device, turn on the circuit breaker and check that the isolated ground receptacle has power. Use a non-contact voltage tester to verify that there is no voltage between the green screw and the metal box or any other grounded surface. Red wires are typically used for isolated ground circuits. Bare wires can also be used for isolated ground circuits in certain jurisdictions. Isolated ground circuits provide additional protection against electrical shock and reduce noise in sensitive electronic equipment. Always follow local electrical codes and obtain the necessary permits before performing electrical work. To elaborate on the materials, the 12.3 non-metallic sheath cable with ground refers to a specific type of electrical cable commonly used in residential wiring. The 12 represents the American wire gauge, or AUG, size of the conductors. In this case, it signifies that the cable contains 12 gauge wires. The 3 indicates the number of current carrying conductors within the cable, typically including a hot wire, a neutral wire, and a ground wire. Non-metallic sheath cable means that the wires are encased in a non-metallic outer jacket, providing insulation and protection. The ground wire is included for safety, providing a path for fault current to return to the source, helping to prevent electrical shock. An isolated ground receptacle is a specialized type of electrical receptacle designed to minimize electrical noise and interference. It features a separate grounding path that is isolated from the regular equipment grounding system. This isolation helps to prevent unwanted currents from flowing through the ground wire, reducing the risk of electrical noise affecting sensitive electronic equipment. A metal junction box, though optional, provides a safer and convenient enclosure for making electrical connections. It helps to protect the wires and connections from damage, while also providing a grounding point for the electrical system. Metal junction boxes are commonly used in electrical installations to house splices, terminations, and other wiring components. Now we can clarify the steps. At the power source, which is the main breaker panel, firstly, identifying an empty circuit breaker slot in the load center is essential for safely adding a new circuit. The load center is the distribution point for electrical power in a building, and each circuit breaker controls the flow of electricity to a specific circuit. Choosing an empty slot ensures that the new circuit can be properly connected without overloading existing circuits. Secondly, removing the knockout plate that corresponds to the circuit breaker location involves carefully removing a pre-cut section of the metal enclosure of the load center. These knockout plates are designed to be easily removed, providing access for installing wiring connections. Removing the correct knockout plate ensures that the wiring can be routed properly into the load center. Thirdly, inserting the 12.3 cable through the knockout and stripping about 6 inches of insulation from the conductors prepares the cable for connection to the circuit breaker and other components. Stripping the insulation exposes the individual wires within the cable, allowing for secure and reliable electrical connections. Fourthly, connecting the white wire to the neutral bus bar involves attaching the white wire from the 12.3 cable to the neutral bus bar inside the load center. The neutral bus bar serves as a common connection point for all neutral wires in the electrical system, providing a return path for current to flow back to the source. Fifthly, connecting the black wire to the load side of the new circuit breaker involves attaching the black wire from the 12.3 cable to the terminal on the circuit breaker that is connected to the load, or the devices that will be powered by the circuit. The circuit breaker acts as a switch controlling the flow of electricity to the circuit and protecting it from overloads and short circuits. Sixthly, connecting the green, or bare, wire to the main ground bar or isolated ground bar if available involves attaching the grounding conductor to the appropriate grounding point inside the load center. The grounding system provides a path for fault current to flow back to the source in the event of a short circuit, helping to prevent electrical shock and equipment damage. Now we'll elaborate on the steps at the device, the receptacle location. Firstly, mounting the metal junction box, optional, at the desired location provides a secure and protected enclosure for making electrical connections at the receptacle. The junction box helps to prevent damage to the wiring and provides a grounding point for the electrical system. Secondly, connecting the red wire from the 12.3 cable to the brass screw on the isolated ground receptacle involves attaching the red wire to the terminal specifically designated for the isolated ground connection. The brass screw is typically color-coded to indicate its function as the isolated ground connection point. Thirdly, connecting the green, or bare, wire to the green grounding screw on the receptacle involves attaching the grounding conductor to the grounding terminal on the receptacle. The green screw is typically color-coded to indicate its function as the grounding connection point. Fourthly, connecting the black wire to the black screw on the receptacle involves attaching the hot wire from the 12.3 cable to the terminal designated for the hot connection. The black screw is typically color-coded to indicate its function as the hot connection point. Fifthly, connecting the white wire to the white screw on the receptacle involves attaching the neutral wire from the 12.3 cable to the terminal designated for the neutral connection. The white screw is typically color-coded to indicate its function as the neutral connection point. Now for verification. Firstly, at the panel, ensuring that both the red and green, or bare, wires are connected to the ground bar confirms that the grounding system is properly connected and functioning. This step is essential for ensuring electrical safety and preventing electrical shock. Secondly, at the device, turning on the circuit breaker and checking that the isolated ground receptacle has power verifies that the circuit is properly wired and functioning correctly. This step ensures that the receptacle is receiving power and is ready to be used to power electrical devices. Thirdly, using a non-contact voltage tester to verify that there is no voltage between the green screw and the metal box or any other grounded surface confirms that the isolated ground system is effectively isolating the grounding path from other grounded surfaces. This step helps to prevent electrical noise and interference from affecting sensitive electronic equipment. An isolated ground circuit is a special type of electrical circuit designed to reduce electrical noise and interference, particularly in sensitive electronic equipment. It achieves this by providing a dedicated grounding path that is isolated from the regular equipment grounding system. Unlike standard circuits where the ground wire is connected to the metal chassis of the equipment and other grounded surfaces, an isolated ground circuit has a separate grounding conductor that runs directly back to the main electrical panel. This isolated grounding conductor is typically identified by its orange color or by the presence of an orange stripe on the insulation. The purpose of isolating the ground is to prevent unwanted currents from flowing through the ground wire. In a typical electrical system, various electrical devices and equipment can generate electrical noise, which can then travel through the grounding system. This noise can interfere with the operation of sensitive electronic equipment, leading to malfunctions, data errors, or reduced performance. By isolating the ground, these unwanted currents are prevented from flowing through the grounding conductor, minimizing electrical noise and interference. Isolated ground circuits are commonly used in applications where clean and stable electrical power is essential, such as recording studios, computer labs, medical facilities, and industrial control systems. In these environments, Even small amounts of electrical noise can have a significant impact on the accuracy and reliability of electronic equipment. When installing an isolated ground circuit, it's important to follow specific wiring practices to ensure proper isolation. This includes using isolated ground receptacles, which have a separate grounding terminal that is not connected to the metal mounting strap. Additionally, the isolated grounding conductor should be run directly back to the main electrical panel without being connected to any other grounded surfaces along the way. Furthermore, it's crucial to verify the integrity of the isolated ground system using appropriate testing equipment. This includes measuring the voltage between the isolated ground terminal and other grounded surfaces to ensure that there is no voltage present. It also involves testing the resistance of the grounding conductor to ensure that it provides a low impedance path for fault currents to flow back to the source. When planning to install an isolated ground circuit, consulting with a qualified electrician or electrical engineer is crucial to ensure compliance with local electrical codes and safety regulations. They can assess the specific needs of the application and recommend the appropriate wiring methods and equipment to achieve optimal performance and safety. In addition to reducing electrical noise, isolated ground circuits can also provide enhanced protection against electrical shock. By isolating the grounding path, the risk of stray currents flowing through unintended paths is minimized, reducing the potential for electrical hazards. However, it's important to note that isolated ground circuits are not a substitute for proper grounding practices. All electrical equipment should still be properly grounded to ensure safety and prevent electrical shock. Isolated ground circuits are simply an additional measure to reduce electrical noise and interference in sensitive applications. The National Electrical Code, NEC, provides specific guidelines for the installation of isolated ground circuits. These guidelines cover various aspects of the installation, including wiring methods, grounding requirements, and testing procedures. It's essential to follow these guidelines to ensure that the isolated ground circuit is installed safely and effectively. When working with electrical systems, always prioritize safety. Wear appropriate personal protective equipment, such as safety glasses and gloves, and use insulated tools to prevent electrical shock. Additionally, always disconnect power to the circuit before working on any electrical components. In summary, an isolated ground circuit is a specialized electrical circuit designed to reduce electrical noise and interference in sensitive electronic equipment. It achieves this by providing a dedicated grounding path that is isolated from the regular equipment grounding system. When installed properly, isolated ground circuits can improve the performance and reliability of electronic equipment while also providing enhanced protection against electrical shock. Always follow local electrical codes and safety regulations when working with electrical systems. Remember that red wires are typically used for isolated ground circuits to easily identify them. Bare wires can also be used for isolated ground circuits, but the rules vary in different locations. Isolated ground circuits are great for protecting against electric shock and lowering noise in sensitive electronics. Always follow local electrical codes and get the necessary permits before starting any electrical work.